Can folks hear me? Is that louder? Is that working? Can you move this? How about that? Is that better? Hi, good to be here. If I get my prop. He's gotten a little fatter through the years, but used to be kind of thin. He's bored. Alrighty. I'm going to talk a little about the Avro project. I try to keep it brief, let you guys go. We're running a little behind schedule. So first, what is Avro? It's kind of three things. There's an underlying bit, which is a data serialization library. And then there's two dominant things that we're building on top of that. One is a file format for data, so to support Hadoop applications. And the other one is an RPC system, an RPC format, a wire format for RPCs. They're pretty separate, used independently, and they share some common technology. And I wanted to be cool and have clip art. So these are all pictures of Avro aircraft. And there's some loose metaphors about where the pictures are associated, but with the subject, but it's loose. This is a pretty cool one, the Avro car. It never really worked very well, but it was pretty cool. They're no longer in production. So existing serialization systems. The big two that are out there that are open source that people know about are protocol buffers and Thrift. They both have pretty expressive schema languages. They're both reasonably efficient. They write data in a reasonably compact form, and they're fast to read and write. They're not terribly dynamic. The primary mode is that you generate code from a schema that then you compile and link and load into your application. So it's hard to, if you've got a directory full of files that you want to kind of look at, it's hard to know what they're in unless there's some separate thing describing that. And if you want to look at a new data type, you can't just sort of click it and double click on it and open it up because you don't necessarily have the description. You have to generate some code depending on what language you're working in. And same thing for writing a new data type. If your program is, for example, dynamically joining two different data types into in some way, you want to be able to dynamically generate a new data type and write it out conceivably. And that's fairly awkward to do with things like protocol buffers and Thrift. So they have some limits in how dynamic they are that we set about to fix in Avro. So Avro's serialization specifies a data format. The way you describe data structures is in a schema language that's in JSON. The reason for using JSON is because we require every implementation to parse the schema language. We didn't want them to have to write a complicated parser. And most programming languages already have a JSON parser. So doing this in JSON makes it easier to implement. So each language just implements something that can read and write data based on a schema. It's fairly straightforward algorithm that's specified where you walk the schema to read and write each instance, and similarly you walk the schema. I guess I said read and write. Anyway, so code generation is optional. You don't need to generate classes for every data type. You can do it. We have code generators for Java, and that's useful. That's some people like to have a dedicated class for every data type generated, but you don't need to. If you're using Ruby or Python, there's really no point in some languages. Another thing to note that distinguishes Avro is that the data is untagged. There's no annotations per field saying which field it is in the data. It's just the raw data. So, for example, a record has a bunch of fields, and adding a record around a bunch of fields adds no overhead. So if you have for example, let's think about a date class. A date, you might represent as a long, as a 8-byte quantity, and you could either have a long field in a data, or you could have a separate data structure, which was a long class or whatever, a separate schema, with a single field of long. In Avro, when you write it out, it's going to be the same size. There's no overhead for nesting that in a record and having a field in it at all. And this is not true of most serialization systems. They end up tagging the data a little bit at runtime, which we managed to avoid. Avro supports schema evolution. The writer's schema is always available to the reader. It has to be available to the reader when the data is read. And the reader can then compare what was written to what it expects. So if the data was written and there's a field that corresponds with the same name and type, or a compatible type, then you can read it. And if it's only compatible, it's not an exact match, then you can convert it, and there's rules for that. But if the data contained a field that you don't expect, you can ignore it. If there's fields you expected that weren't written, then you can identify that, and either if you require it and you don't have a default value specified, then you throw an error, or else you use the default value. These are pretty much the same features that protocol buffers and Thrift do. They do them with numeric field IDs that you need to assign in the records rather than the names of the fields. So it's a little nicer. It's all symbolic, but it's the same general principle. And as people often note, it doesn't solve every backwards compatibility problem. It just gives you kind of a leg to stand on to solve backwards compatibility problems. It solves a lot of simple ones, adding fields or removing fields, but if you change semantics deeply, then you're going to need to make sure you handle that. So some examples of schemas. Here's two simple schemas in JSON. First one is a block, a simple record, 3 fields, ID, which is a string, length, which is an integer, and an array of strings called hosts. I hope that makes sense. Pretty straightforward struct. A lot of quotes. Sorry, that's Jason. Second one is a little more interesting. It's a list of a linked list of either strings or ints. So it has one field whose type is a union. It can either be a string or an integer. That's indicated by the square brackets, are union types. And then this shows you can have recursive data structures. So that it has the next element is itself a my list. So that's representing a linked list. Does that make sense? Seems to. All right. So Todd Lipkin implemented a higher level syntax for people who don't like JSON, which we call Avro IDL. And so these are the same schemas written that way, a little easier to read. Look a little more Java, C++-like. So here you can see, the same thing: a string, an int, and an array of strings in the block record, and in the list you've got the union of string, a string and int, or a pointer to the next. All right. So moving along. So now we talked a little about the underlying serialization technology. Now I'm going to talk a little about data formats, using this as a data file format. Today in Hadoop, primarily folks are using text files, often compressed with gzip or LZO. Text files are very interoperable. It's a long tradition of using them in Unix. Just one line equals one record. But they're not terribly expressive. If you've got CSV or something like that, you need some convention for naming the columns. If you want to add a new column, how do you indicate that? So it's a little fragile. It's also not terribly efficient if you're doing numeric data, unless you throw binary data into a text file, which is kind of ugly. People do it. But, then the other thing that's commonly done in Hadoop is are writables. Very expressive. You can do arbitrary Java data structures. Can be very efficient. You can write efficient binary input and output. represents integers and floating point numbers and things like this in compact ways. But on the downside, they tend to be platform specific or Java specific, not necessarily easy to read from C or Python or Ruby, and unless you go through a lot of work, they are very fragile. If you add a field, remove a field, you may have trouble reading the prior version of the data structure. It should be obvious how we can apply the previously described Avro technology to this. We can get the expressive schema language. We get small and fast data structure, small and fast format for the data, and moreover, it can be dynamic, so that you can pick up files that you've never seen before and look and see what the fields are in them and deal with them. But we're also factoring the fields out of each instance to keep them nice and small. There's a file format defined in Avro. It's roughly designed to be a replacement for a sequence file. There's also a text encoding defined, so you can take a file and put it out as plain text, so you can view it sort of for debugging. It prints it out as JSON. There's, as I mentioned earlier, the handling of versioning of the data. And we're generally hoping that folks will start to use this as a standard file format for data and replacing sequence file and text files. I mean, trivially, you can replace text files with just a file of byte arrays or text arrays, depending on your thing. Just a simple record with no structure in it. Ideally, you'd want to model the records in it better, but even with that, you can get a leg up on gzip because the Avro file format is splittable natively, and it supports compression internally, so it's got those advantages of sequence file. So I'm going to now talk about MapReduce API, which has recently been added to Avro. It's slightly different than the normal Hadoop MapReduce API. In particular, it has single-valued inputs and outputs instead of a key and a value separately coming out. So you only need to have key-value pairs for the intermediate data that you pass out of map and into reduce. So roughly speaking, the map signature takes an input object and a collector of output objects. And so if you're doing a map-only job, for example, you never need to create key-value pairs. You can just work directly at that level. If you're going to feed and reduce with your map, if you're really writing a MapReduce program, then you need to have your output be pairs. So pair is a class in the Java API, and it's an Avro schema that pairs together two other schemas, a key and a value one. And so then the map signature looks like you take a map, you get an input object, and you pass a collector of pairs of key value objects. Reduce then will get a key and then an iterator over all the values, and then a collector of outputs. By default, if your input and output happen to be paired data, then it will do a sort as is customary in MapReduce. That makes sense. A lot of Avro's data file just has a collection of records, not a collection of key-value pairs like sequence file, and that's commonly the case. That's like files which are lines of text are really files of records and not key-value pairs. And we have some conventions for breaking those into keys and values. But here the approach is to try to do that in the map function itself, to do that assignment of what is a key and what is a value. So this is this API for Avro data files doing MapReduce is in Avro's trunk today. It builds on the Hadoop version 20 MapReduce APIs, which I think I haven't tested this, but I believe it should work even on Hadoop 18. It doesn't doesn't use anything very exotic in the MapReduce APIs. And it should also work in 21 and 22 even, because the Hadoop 20 APIs are going to stay around here for a while. And it should be released in Avro 1.4, which will come out next month. So here's an example of the old classic word count. So a lot of this should look fairly familiar. We get a string tokenizer, we iterate through the tokens, and we collect pairs of token and one. And then in reduce through the counting, we just iterate through the counts. So we get the iterator there. No, we get directly a long Java data type. And we sum them, and then we collect output pairs. So it's fairly straightforward how that all works. So moving on to RPC. So again, this builds on the base serialization technology, so you can have the same back compatibility guarantees. A message itself, a procedure call, is modeled as a record, so you can add and remove parameters to messages, and you have the same rules for how those are handled and defaulted if they're missing or added. And we're hoping that, again, that this will be adopted by Hadoop. It's a long-term plan. It'll be a big move for the system. But what it will permit is let applications talk to clusters running different versions. It'll let us do features like rolling upgrades of Hadoop clusters. You don't necessarily have to take down everything and update it and rebuild all your applications to use the new version before you can upgrade. It lets you run things that are slightly mixed, which should be useful. And longer term, provide cross-language access. So it lets you do things like have a native HFS client in C, which would be a useful thing. So here's an example in the Avro IDL of an RPC protocol. Defines a record that looks a lot like records before. No, not coincidentally. And here we define a simple message. So one parameter, which is a greeting, message hello, and returns a greeting. And so in Java, for example, there's you can generate code to define the interface for this and do clients and servers, and that all works. So current status, there's C. There's support for C, C++, Java, Python, and Ruby. Reading and writing data and doing RPC. The MapReduce API is in Java. There's a plan to do something that's sort of like pipes. It's a lot like pipes, if you're familiar with the Hadoop pipes for C++, but to pass Avro data down to a sub-process so that folks can write mappers and reducers for Avro data in other languages like C and C++ and Ruby and Python, and not have to go through a plain text format, doing it line by line, but actually passing down the raw data structure and parsing it in, building it up in those languages. One advantage of this approach is that Avro lets you specify for each schema. I didn't talk about this earlier. How it is ordered in the schema. You can define how you compare it to other records, so if you're writing a MapReduce program in another language, you don't have to write a raw comparator or any kind of comparator for your data in Java, nor do you have to spend a lot of time trying to arrange that the binary format of the data sorts well. You can actually declare how it should be ordered in the data structure, and then the MapReduce engine will sort it as you need it. So we need to get these, as I mentioned, these other MapReduce APIs implemented. That should come soon. The RPC is starting to get used a little here and there. We heard about it being used earlier in a Yahoo system. The Flume system is beginning to adopt it. I think there's an interface for HBase that's beginning to use it, and we're hoping to see it roll into more and more projects as time goes on. That's pretty much it. I've got us almost back on schedule. Questions? Yeah.
So I came across another framework called Message Pack. So can you compare Avro with Message Pack?
What I know about Message Pack is that it looks like a good system. I don't know what language. I don't remember what languages it supports. The data structures, the data model is. Pardon, David?
It supports 6 languages so far.
6 languages. Okay. The data model is much more like a JSON data model. So you don't have named data types. So you have a record, but the record doesn't have a name. So you'll never generate classes, which might be fine. You're always operating on a generic kind of a data structure. I think it's been written since I started Avro. So I heard about it the other day. They also the data format tags the data, and in fact it's fully tagged. There is no schema. So if you have a file of records, each record could be completely different, as far as I understand it. There's no declared schema for a file. Rather, there's tags. Now they have a very efficient tagging system, so they only spend a few bits saying whether it's a signed int or whatever it is, and how many a record with how many fields and so on. I don't know how they do the record field names, how they keep those, because I think those can get big if you're repeating those. I don't recall. There's some trick I think to managing that. So it's a slightly different take on things. One thing that also tends to distinguish Avro is the union type. A lot of things don't have that, and I don't know if they have something like it. Well, I guess you don't really need a union type in that sort of data model.
Based on drift IDL, so from magnetic from drift to.
So they use drift IDL in it?
Yeah.
Oh, really? Okay, I didn't realize that. Anything else? Yeah.
So sequence files already feature zlib and gzip compression, I think. And so, what are the advantages of Avro's compression capabilities?
I mean, it uses gzip compression currently. We're going to add fast LZ to it soon, rather than LZO, but it's comparable. So there's no specific advantage in the compression. The advantage is that you have a format that you can write from other languages. So if you've got a process that is taking log files and putting them into HDFS, and you want to have them in a format that you can read them with MapReduce jobs, it'd be nice if there was a C program that could create these files easily. And you can't create a sequence file in C easily, whereas you can create an Avro file in C. So that's the advantage. Advantage there against sequence files is it's mostly the language interoperability. You can create them in one language and read them in another. I mean, moreover, depending on what you're putting in the sequence file, the data structure, you might not be able to create in C to get started. Anything else?
Yeah. So sorry. So for storage and for RPC, right? So if there are issues which basically favor RPC versus storage, or storage versus RPC, which way is Avro leaning? Is it targeting towards RPC or storage?
I think, well, that's a trick question. I think the features that distinguish Avro from other serialization systems are more salient for data serialization, for data files, than for RPC. I think it's the dynamic abilities are more convenient there than in RPC, where you tend to not need the dynamic stuff as much. But yeah.
Seems like there's still a lot of inertia going towards regular text files. Do you have a plan for really getting people to adopt it across the board?
I don't know if people heard the question. A lot of inertia towards plain text files. Is there a plan to get those people to adopt Avro? What we'd like, I mean, the dream is that we can get good C utilities, a C command line that is a lot like the gzip program that will take a file which is a text file and produce an Avro file with that data. And similarly, if you've got a CSV text file, then you can give it the field names and it'll produce an Avro one. The more you can tell it, the smarter it can be about how it compresses it and how much it, how it represents it, so that other programs can deal with it. So we could have something that would ingest Apache logs and put them directly in this. The problem with a big gzip file is you can't split it. So having there isn't a good native Unix file format that's splittable. And so we'd like to, the fact that we have a C version of Avro means that we could write a good, simple utility that is, and have a language independent file format that can, to some degree, replace things like gzip. So I don't have a grand plan other than, hope. Anything else? Last question? Yeah.
Is it possible to build a type hierarchy like in C++?
What do you mean by type hierarchy?
In your schema, can I have inheritance, polymorphism?
Can you?
Inheritance, polymorphism.
There isn't inheritance. You can no. There's no provision for inheritance at this point. You can in some ways fake inheritance with unions, but no, there isn't. And polymorphism. You could get some things that are like that and model most things reasonably well by using unions, but there's no inheritance currently provided. All right.